this paper, where the data were actually synthetic, but they were synthesized by a researcher, maybe a couple different researchers who had been given access to the real data, but because this data set pertains to these like apps that you download, and then they like collect a lot of data about how well the insurance or insured people drive, and then they charge premiums based on that information, so that they had an actual data set and they were able to do a lot of supervised learning-ish stuff to construct a data set that ostensibly had the same structure. In order to do things with that, first you need to put things into some same units if you want to use them. Also, there's a variable with some spaces in it that does not work, so we change this. Make it run a little bit faster. We'll only use 10,000, but there's no reason why should be limited to that. And so, if we then do like a Poisson model with a spline on the age of the insured driver, a bunch of other things pertaining to them, inclusive some stuff that would be routed by the app. It could also be useful to include an offset in the model as to the number of time periods that the person was insured, so that we can interpret this as sort of number of auto insurance claims per year rather than total number of auto insurance claims, without regard to how many years you've been driving. Poisson, some fairly weakly informative priors on stuff, except the intercept actually made it fairly negative, because it's for any 1% unlikely that they're going to be having an auto claim at once. Talk about this divergences thing a little bit today, but anyway, it runs. You get out a plot that might look something like this. In the case of if you did the spline on age, and this is actually consistent with well, it's consistent with a lot of things. It's certainly consistent with it being a straight line in log units. But the uncertainty is fairly 95-90% interval on the unknown function is fairly wide, or not fairly wide. The units of the vertical axis. So this would be in like claims per year. So if 5%, something like that. Anyway, it's definitely consistent with it being a line that's maybe a little bit downward sloping, but it could be even more something like this that can't be ruled out just because we don't have a whole lot of data on people who are 8 decades old driving around. So it's good to leave these sort of nonlinear structures in, propagate your uncertainty as to what the function is to the estimates of everything else that you might be interested in, like the stuff that comes from the app or whatever. If you estimated a GLM, which is what most people would do, including sort of the authors of the original paper, although I think they had some penalization stuff going on in there, then the estimates that you get, for the stuff maybe that you care more about, are conditional on this being a straight line, as opposed to marginal over all the things this function could be. And like a lot of things in the social sciences, this is, I guess, kind of economics. But like a lot of things in the social sciences, you have no justification at all for assuming things are linear. So that's point number one. Point number two, you have no justification at all for assuming these sorts of relationships are crazy. Like, that is not consistent with anybody's understanding of aging. And so between those two things, you know, we have probably a lot of situations in the social sciences where the relationship is like almost linear-ish, kind of quadratic in nature, not like actual quadratic, a plus x squared plus b times x plus c, that would, you know, be perfectly, you know, this shape or that shape, but maybe like a squashed version of quadratic where, you know, things turn once. Maybe in some circumstances we could, you know, think of a situation in which, you know, for something like age or income, it might go up and down and then again, and then maybe up. But we're sort of, in the social sciences, thinking about functions that are almost low degree polynomials, but not quite. And I think that is what we should be using a lot more of, but that means you're going to have to do a Bayesian, because the frequentist estimator of spline, well, the maximum likelihood estimator of splines is terrible. If you introduce like 20 additional columns in X based on different nonlinear functions of the age variable and just do maximum likelihood, one, you're going to massively overfit the data that you have. It's going to give you terrible predictions for future drivers, and if you're getting terrible predictions as your insurance company, you're going to go bankrupt. So they don't even, maximum likelihood of spline models is not even a thing. If you're going to do this frequentist at all, they're going to be like, oh, let's do penalized maximum likelihood, which is essentially supervised learning. But all that does is shift the mode over. You still only get like one function out, as opposed to a distribution over functions. And thus your predictions that you make are conditional on the one function that you get out, as opposed to marginal over all the functions that this could be. So really, to estimate these sorts of models of Bayesian machinery with MCMC, where you get draws of functions, or draws from functions that you can plot like this, is really the ideal way of doing things. Or, yeah, doing things in general, but in particular for estimating. Unknown, nonlinear, but assumed to be smooth functions. So questions about the first one there? Yeah.
Sort of conceptual questions. There are like a couple of different things here that we could run the spline on, and it seemed like adding the spline increased the time it took to estimate the model. So I was just wondering if, like, is the best practice just to do a spline for everything that's like potential linear predictor, or to do them one at a time and see which one is the best nonlinear shape and then use?
Yeah, we'll talk a bit later today about how you can go from a model that maybe has like too much nonlinearity to a simpler model. But I would say yes, you should be open to the possibility that any of the numerical predictors that you have could have non-linear relationships, particularly because like this is, you know, the function is in a logarithm of expected auto insurance claims per day, which is like a not linear function of the actual data. So it would be just like a miracle if like it turned out to be exactly aligned with contradictory nonlinear functions applied to make the thing where the line intersects it. So yes, you should definitely be open to like anything could be a little bit nonlinear. And you should do things like ELPD, posterior predictive checks, etc. If you have a lot of data, like it's fine to estimate a lot of nonlinear functions. It's just going to take quite a while. And another thing is that okay, I just put one in here for the sake of illustration. The S function allows you to put multiple numeric variables into it. So if you put in two variables, you could be estimating a bivariate spline that has an interaction between the two variables that you put in. You can put as many variables as you want into it, like that's valid syntax. It's going to create a ton of columns of X. And so you need to be having like a pretty, definitely proper, but fairly informative prior on those coefficients that go into that, and they have an expectation of 0 into the prior, but you're estimating the standard deviation, and the bigger the standard deviation, the more wiggly the function is. And so as you do these more complicated things, it can be more and more incumbent on you to put informative prior on the standard deviation of the wiggliness. You get exponential or whatever, but increase the rate, decrease the expectation, and so you're putting most of your prior beliefs on fairly straight functions. And at that point, your effective number of parameters is not super great, which you can see again with the video. So anyway, those are available. If you're doing any serious research thing, if you need to let it run for a week, it's going to take longer than a week for the reviewers to get back the comments. So just do it. But this, more generally, okay, these are taking a while to run, and there might be some penalized maximum likelihood thing that runs in 5 seconds, and a lot of people look at that and say, I could take 5 seconds, or it could take 5 hours. Which one do I want to choose? But the fact that it takes a lot longer with the Bayesian thing, you always have to keep in mind that the Bayesian, algorithm, MCMC, is trying to do something much, much, much more ambitious than go to the mode of some penalized maximum likelihood thing and stop. Go to the mode and stop takes 100 function evaluations or something like this. Go throughout the entire parameter space in proportion to the posterior density is a much more ambitious thing. And it takes millions of evaluations of the kernel function to get this right. And that takes a long time. And particularly with the more complicated models like this, Stan has to take smaller steps throughout. And so it has to take more steps when those steps are smaller in order to get around the whole posterior distribution in this, nominally speaking, very high dimensional parameter space. So every column of X gets added as another dimension to this parameter space. So it's going through, 100 dimensional or whatever parameter space, taking small steps in order to give you back draws from the whole posterior distribution that are in proportion to the posterior density in that region, and are not super positively autocorrelated with themselves. And so you get a decent effective sampling size. And that is just orders of magnitude of more of an endeavor than use the algorithm that was created in 1970s to go to walk locally up a hill and then stop and give you back one number that doesn't adequately capture the entirety of it. But anyway, so you can do those. Other questions about this one? Yeah. Okay, my zero inflated one, I messed up the cache, and so it wanted to run this again just when I got here, so I didn't have time for that. But anyway, I think what you should have found, depending on what model that you did, that you don't really have a zero inflation problem in this situation, although there's plenty of reason to think that you might. Some people don't drive their cars every day. Maybe they only drive on weekends, like they walk to work, you know, whatever. So you're gonna have, when you have zeroness, you're gonna have that as being a mixture of people who just don't drive very often, in which case they don't have a whole lot of traffic accident claims. They might if their car gets like broken into, or somebody crashes into it while it's parked on the street, or hail damages it, or whatever. But anyway, you know, if you don't drive that much, you're not gonna have that many traffic accidents. So you've got those zeros, and then you've got zeros from, you know, people who drive more. They just drive really carefully. And so they have a low probability. And so you could have a mixture of zeros. But at least in this synthetic data set, depending on the model, that might be unnecessary, even though in this situation, if we have a good, or what seems like it would be a good predictor of, do you have positive auto insurance claims or zero auto insurance claims based on the number of years in the past that you've had no claims. And so, yeah, if you don't drive very much, you know, you could go into that. So, like, it's a totally plausible model, but because the counts, even with just the regular Poisson, the expected count of the number of claims is fairly low, that's not too inconsistent with a regular Poisson. And so you might have found that with the Lou comparison. Also, what you should have found with the Lou comparison is that the expected log predicted density estimate that you get from Lou should be a pretty good estimator of the expected log predicted density in the testing 10,000 observations that you held out in the testing data. Not that you should do that, but that it illustrates this idea, which is close to dogma in supervised learning, that you have to split your data into training and testing and make your evaluations as to which model is best using the testing data only, and the testing data should not have any contribution to the estimates. It means, from a Bayesian perspective, the testing data is wasted. Completely wasted. You could have used all the data, conditioned on it, and got a more precise estimate of this function and everything else. And then you can use Lou, Pareto smooth importance sampling, Lee one-out cross-validation estimator of the expected log predicted density to estimate, you know, how well this model would predict future data of the same size. And so you don't need to split into training and testing in order to estimate the ELPD. The ELPD estimator is fine because it asks what would happen, what if we left out the first observation, refit, predicted it, you know, count it all up, do that for each of the observations. And so, you know, in this case, there are no warnings or whatever to suggest that that estimator was invalid, and so we don't actually have to refit anything in order to estimate, you know, in-fold cross-validation, which is essentially what the one-out cross-validation is. And so we're free to use all the data that we can get to condition on, to get the posterior distribution as, you know, precise as possible for making inferences, about this, or anything. And so that's a consequence of like a lot of things, that we've built up, but it's a very important one. That you should not be splitting your data. If you're doing Bayesian model. The splitting business is to mitigate the consequences of supervised learning's choice to use numerical optimization rather than sampling to estimate. And it's a consequence of the fact that overfitting phenomenon that splitting into training and testing is designed to protect against is to first order due to numerical optimization. And so you're mitigating a problem that you created for yourself when you do, lasso or elastic net, whatever these things are. Questions about that first one? No? Some more? Okay, and then, the general social survey, which, a lot of people in the QMSS should be familiar with from some of your other classes, it actually, for this last presidential election, you could link it together with the American National Election Survey, which we've also talked about before. It happens, every 4 years. And so same people were asked questions at like multiple points in time, and then they were also asked questions about, after the election. And so, I did a model where some of the predictors were how much the person thinks the government should be funding scientific research, which became extraordinarily controversial during the pandemic, or the start of the pandemic. As predictors, the terminal degree that the person has, their age, and then the outcome is this ordered thing as to whether research on vaccines is greater than the risk or whatever. So this has 7 categories here. Really good. And then we could use BRM to estimate a model like that, saying that there should be a monotonic relationship between the degree, less than high school, associate degree, bachelor's degree, graduate degree. And also, more for the sake of illustration, allow the effect of age to differ depending on how much the person thought the government should be funding scientific research in 2016 or 2018, whenever it was that they were asked that question, before things got all thrown out of whack. Pandemic, so you guys made that. I left this in because I want to show what you want to do later. But this is, not good. It does have a link here that you can go to that has some more information, but we'll talk about that. So anyway, we get a whole lot of warnings with this. But you can plot the ordinal relationship that was assumed. But the fact that it was monotonic was assumed. The fact that it's exactly this shape was estimated. So people with graduate degrees have much different opinions on this question of are the vaccines worth the risk deal than people with high school and less than high school. And then frequentist models. So they're used a lot in some subfields and used like never in other subfields. But just because something is used a lot or not used a lot doesn't really tell you a whole lot about it. They really should be used in the situation where the grouping variable has been randomized as part of the design. design. And that happens sometimes, such as with cluster random sampling. It doesn't happen that much, particularly in political science, economics. I don't think it happens very much in psychology or sociology either, because the people that they have in their studies are often not even random samples at all. But it's certainly not the case for like this question that was asked before the pandemic: how much do you think the government should be funding scientific research? And a lot of other situations in which you'll see hierarchical models being used. And in those situations where they do something like, they put the country in as a random effect. Best case scenario for that is that they're estimating a dubious approximation to a Bayesian model, assuming the posterior distribution to be normal, conditional on the data. But that's not a reason why you should do that. It's a reason why you should estimate like an actual Bayesian model with actual primers and get actual draws from the actual posterior distribution to do this sort of thing. And so that's that. And this distinction is drawn because when you do this with maximum likelihood, the likelihood function being maximized by frequentist estimators, so LME4 in R, Stata has a similar thing, SAS has SAS prop mixed or whatever, to estimate a so-called mixed effects model that includes both random effects and mixed effects. Anyway, likelihood function being maximized by those things integrates out the A sub j's and the B sub j's. So the shift in the intercept by j group, or the shift in the slope on some coefficient, on some variable by j's group. So it integrates those out like we've done a few times. Integrates them out of the likelihood. That can be done analytically if the original likelihood function is normal. In this case, with ordinal, it's not even possible to do that integration analytically. So they have to approximately integrate. And actually, the best way to approximately integrate is to use MCMC. So then you're basically just pretty much doing Bayesian thing anyway, except without explicitly saying what your priors were, and except not getting out a posterior distribution. You're just getting out this point. But anyway, analytically or numerically, they integrate out these A's and B's from the original likelihood function to get a new likelihood function that only depends on the common parameters, the alpha and the beta and the sigmas and all that. And thus, the maximum likelihood estimates that you get out are irrespective of the grouping structure, marginalized over the grouping structure, not in any way, shape, or form conditional on the grouping structure. Because from a frequentist perspective, the grouping structure is like noise. It's an obstacle to getting consistent estimates of the alphas and the betas and the sigmas, because like the big units were random. Like you could have easily gotten a different set of other big units if you repeated this over and over, and those other big units would have had different A's and B's, so it's just marginalized over all of it, make inference about the alphas and the betas. And so that stuff is not estimated. You can get predictions of it by maximizing the integrated likelihood function, get point estimates of alpha and beta, whatever, form linear predictor, apply the inverse function to it, get residuals by subtracting that from the outcomes. If it was an actual numeric outcome, you can't even do it or no. You could get residuals, and then to make predictions of the A's and B's, it does like another regression of the residuals on the grouping dummy variables. And so they're not estimates because they're a function of the point estimates of the A's, alphas and the betas that are actual population level parameters. So as a result of that, you can't do really like standard errors of the A's and B's because they're not estimated. They don't have a distribution and repeated sampling. And so you can't really make frequentist inference about these. In contrast, Bayesian models, especially including hierarchical models, you just condition on the data that you have. You should think about how the data came to be, or how it came to be in your possession, when thinking about a generative model for that. But the estimator that you use is going to be the same either way. And with a hierarchical model, at least those in RSTN, RMB, RMS, etc., we're going to condition on the grouping structure. And the parameters A and B are just as much parameters as anything else. We have beliefs about them going in, we have beliefs about them coming out. We draw from the posterior distribution of them along with all the other unknowns, conditional on the data. And so if we want to, we can make probability statements about the A's and the B's, or functions of the A's and the B's. We can posterior predict with draws, using draws from the A's and B's. We can even do that for new units. All sorts of stuff like that. But if we don't care about those things, then we don't have to use them. They're just columns. So Bayesian hierarchical models really are different. They use a different likelihood function than what frequentists do. Bayesian hierarchical models use the likelihood function that frequentists start with. Frequentists change it by integrating out the A's and the B's. So we're talking about a different likelihood function in addition to the inclusion of priors in the Bayesian sense, which is often good. Like it came up thing on Ed discussion last week sometime. Anyway, as you get into hierarchical models, even relatively simple ones, but definitely when you get into complicated ones, you find that the maximum likelihood estimates for the sigmas or the correlation between the A's and the B's, etc., take on edge values a lot. So you'll estimate some standard deviation to be 0, or you'll estimate some correlation to be like +1, or something that doesn't even really make sense. And then, the people who use these estimators are like, oh, I'll just take that part out. And it's like true that the maximum of the likelihood function that they are maximizing is on the edge of the parameter space. So the most likely data set to observe when like sigma is 0 or whatever is the data set that was observed. But especially in those situations, point estimate of a parameter like sigma or rho or whatever is an insufficient summary of what you should believe about those parameters, conditional on the data, particularly in a Bayesian model where we condition on the structure instead of marginalizing over it. So yes, maybe the mode is at 0, but everything that's not the mode is to the right of 0. So the median is well positive, the mean is super positive, the maximum is positive. Everything except the minimum is positive. And we can use that to get posterior draws. So I've often said that not that you should do this, but posterior means or medians from RSTN, RMB, RMS or whatever are better point estimates in hierarchical models than point estimates from frequentist hierarchical models are. But there's no reason why you should limit yourself to a point estimate. Like you've got 4,000 draws, and it took over 200 years since Laplace formulated Bayesian inference to get to the point where we could give you 4,000 draws from a posterior distribution that have negative autocorrelation a lot of the time, so the effective number of draws is even greater than 4,000, even though the nominal number of draws is 4,000. Why would you throw away all but one of those draws? Now that makes no sense, but you would be it shouldn't be shock, but like, if you go to a lot of people who may have had graduate training in statistics, maybe not, and ask them, okay, you're going to estimate something. Would you rather have one number or one probability distribution? Almost everybody would take the one number. And those people are like a disaster in terms of making inferences about it. Like the answer to the question, would you rather have one number or one probability distribution? It's obvious you should take one probability distribution. That gives you a much richer answer that encapsulates your beliefs about all the parameters. But the vast, vast majority of people would be like, yeah, I just prefer one number than like a function, a distribution. I don't know what to do with that. Okay, well, let's change the question. Would you rather have one number or 4,000 numbers that were draws from the probability distribution that you said that you don't want? And so now, you know, whatever you want to do with your one number, you could pretty much do just as easily to each of your 4,000 numbers. And now you have a thing that you can plot like this. Would you rather have one number or 4,000? Almost everybody would rather have one number than 4,000. And that's exactly wrong from a scientific or any sort of inferential perspective. But that's a problem with them, not with the method that produced the 4,000 draws from the posterior distribution. So anyway. More questions about that? Okay, so let's see how we're doing here. Still. Hey. This cache got messed up also. Okay. Let me send myself the HTML of this. Hold on 1 second. Alright, so let me just try to show this off of the community file. So as usual, disclosure statement. Should probably internalize that by now. And estimator that's talked about a little bit in the McElwee 3D is 2 stage least squares. And so 2 stage least squares is an estimator of instrumental variables model that is extremely common in economics. It's arguably the probably main quantitative estimation technique that is essentially originated or at least popularized in the social sciences that has come to be used elsewhere outside the social sciences. It's extremely common in economics. It is probably the plurality, definitely the plurality, maybe even the majority of empirical papers in economics using 2 stage least squares, and part of the reason for that is that it has relatively simple procedure that is implemented in essentially all software, which is you use ordinary least squares to estimate the or make predictions to get the coefficients or whatever, and then to predict the causal variable that you're trying to estimate the treatment effect of. And when doing that, you need to include all the other predictors, including the instrument or instruments. Usually there's just one instrument, which is a variable that predicts predicts the causal variable, but conditional on everything else. Does not predict the outcome variable. And then you use the fitted values from the first stage in place of the causal variable. When using ordinary least squares to fit the outcome, conditional on the predictions from first stage in the causal variable and all the other predictors, but not using the instrument and not using the actual causal variable, only using the fitted values from the first stage. And it's like a proxy for the causal variable. And so it's a problem that people's thinking about the idea of instrumental variables and selection and other things that get in the way of causal inference are all tied together in this one estimator of a model that's not even a good estimator on frequentist graphs. So it's not unbiased. It does get less bad as you get more and more data. But unfortunately, like with a lot of things, frequentist, you say, okay, there's an asymptotic justification or rationalization really for something. And then researchers go and they apply that estimator irrespective of how much data they have. So almost no, economist or anybody else is like, I don't have enough data to apply this asymptotically justified estimator. They just do it anyway and then see what the results are. So this estimator, it's not unbiased. It gets less bad as you get more data, but how bad it is for a given amount of data depends on characteristics of the data generating process. So you can't just look at the number of observations that you have or the number of predictors you have and come to some conclusion in advance as to how well this will work. It depends on what the true coefficients and variances and stuff like that in the population are, which you don't know. That's what you're modeling. And so you don't really have a sense of how well or poorly it's going to do in finite samples. And your attempts to figure that out from the data don't really work well because they're based on your possibly horrible plug-in estimates of the things that you don't know. But this first, predict the causal variable with all the other predictors, including the instrument, then use the fitting values to predict the outcome, blah, blah, blah. Sounds like it's the start of a generative model. First stage, second stage. It sounds like a frame of bowling. First roll, and then depending what happens on the first roll, that affects the probabilities and whatnot for the second roll. So this idea of using instrumental variable in the context of a generative model is not too much of a stretch. And so in math notation, it would look like this: treatment variable and outcome variable distributed bivariate normal. Mean for the treatment is unknown, mean for the outcome variable is unknown, standard deviation for the treatment is unknown, standard deviation for the outcome variable is unknown, and the correlation between the errors when predicting those things, unknown parameter rho. So we're going to have, proper priors on sigma 1, sigma 2, and rho. And then for the first expectation, so the first stage, even though from a Bayesian perspective, everything's one stage. There's no, I do one model and then take something with a posterior distribution and then condition on it. And it's like, it should all be simultaneous. But anyway, we have a specification here for the conditional expectation of the treatment variable, intercept, and then coefficient multiplied by the treatment, the instrument variable, z. You can center it, whatever, so you can interpret lambda is the expected treatment variable when all the predictors, including the instrument, are average as opposed to when they're all zero. And then, weighted sum of the other predictors with coefficients theta. Normal prior on intercept. You can have a normal prior on zeta. I think that's what that letter is. It shows it to be similar to z. You can have a normal prior on that coefficient, but you should really have a pretty informative prior on that coefficient, because in order for instrumental variables estimator to give you pretty good estimates of the thing that you want to estimate, it needs to be reasonably strongly associated with the treatment variable whose effect you're seeking to estimate. And so if you're fortunate enough to have one of those variables, z, you really should have pretty specific beliefs as to whether that is positively associated or negatively associated with the treatment variable. You shouldn't have like a so-called instrument and be like, I don't know, it could be positive, it could be negative coefficient. Almost by construction of the research design, you should have beliefs that are on one side of zero or the other, basically. Like if you're ever in a situation where, like, I don't know if this is positive or negative, it's not going to be a good instrument. It's not even a valid instrument from a frequentist perspective. Frequentist requires monotonicity. Anyway, you can have normal coefficients on the other predictive variables. And then in the other part, for the expectation of the outcome, you have intercept, you have betas, they get multiplied by x's, you have priors on that stuff. And so it's basically just doing two linear models. But we have the additional parameter rho that we're estimating for the correlation between those errors. And you might look at something like this and say, well, okay, it's essentially doing twice what we've already done once, many times over the course of the semester, but where's the estimate of the treatment effect? That's why I'm doing this. How do I get a causal estimate out of something like this? And that follows from the generative model that I put up there. And if the treatment variable and the outcome variable are distributed bivariate normal jointly, then the outcome conditional on the treatment is distributed normal with conditional expectation equal to original marginal expectation plus sigma 2 divided by sigma 1 multiplied by rho multiplied by the difference, or the residual, the error, between the treatment and the expectation of treatment that's implied by the instruments and the other predictors. And we use that, and standard deviation is also going to be, take the original standard deviation of the outcome, scale it down by square root of 1 minus rho squared. And so that we use, I remember when we used it on the homework, or no, midterm, about the airplane. We constructed a bivariate normal from, marginal normal on one thing and then conditional normal of the other. And this is what we use for the updated conditional expectation and the conditional standard deviation. And so consequently, the causal effect that we're looking for, at least under our model, so this is all under the model, is this, sigma 2 divided by sigma 1 times rho. But frequentist estimators are not constructed that way, because when you have this nonlinear function of parameters that you're interested in, it doesn't really suffice to just put in point estimates of those things and say, like, that's a good point estimator of delta. But if you have posterior draws of those big things, you can compose them I said, you're gonna want to have, or you really should have, if you're using this sort of thing, an informative prior on the coefficient that relates the instrument to the treatment variable. And, when you go to like econ seminars or whatever, somebody's given a job talk, something like that, they'll say, okay, here's my outcome. I used instrumental variables, 2 stages squares. Here's my instrument. And that takes about 2 minutes of the talk. And the other 58 minutes of the talk consists of people questioning whether this is a valid instrument. Does Z actually not have any relationship to the outcome conditional on the X's? Or does it have a sufficiently strong relationship to the predictor? And the poor person, trying to get a job or whatever, spends 58 minutes of their hour talk defending their beliefs, essentially, about the unknowable, which is, this really doesn't have an effect on the outcome conditional on the prediction, stuff like that. So the whole thing is basically arguing about your beliefs. In which case, if you're going to do that, put your beliefs into the model via the prior. So you really should have an informative prior on this coefficient, puts almost all the probability on one side of the other is 0. Another thing you could, and you probably in a lot of situations should do, is have something of an informative prior on rho, the correlation and the errors between the two parts of the model. So one, that correlation really shouldn't be too extreme, but also rarely are you in a situation where it's like, well, I know the errors are correlated, but I'm not sure if they're like positively correlated or negatively correlated. In most of the situations in which you see 2-stage least squares, it's presumed, not like assumed, but based on the design or whatever, that the errors are usually going to be positively correlated. So if you're talking, we'll do an example. But anyway, and so, but if you do this with the generative model, that's one of the things McElreath says. Like the generative model implies the likelihood function, and the estimator of the causal effect just falls out of that from doing what Bayesian should already be doing. And you can use the same MCMC algorithm that we've been using this whole semester, and you should, by now, become pretty comfortable with using it, for the other models. And then once you have posterior draws of these things, you can get posterior draws representing the beliefs about delta under the model. So being Bayesian doesn't really excuse you from the requirement that you have to defend your instrument. So all the same thing goes in that. But it does give you the opportunity, when estimating this, to put your beliefs about the relationship of the instrument to the treatment variable into that coefficient there. And also your beliefs about whether the errors are positively correlated or negatively correlated into your prior on. So in that sense, it does give you some opportunities, and that gives you a way to obtain a different and better estimator. So I can do this probably. So these data are from a famous example of instrumental variables by Josh Ingres and Alan Kruger, where they got data on people's log of their weekly wage, their number of years of schooling that they have. So these are for more like, working class sort of jobs, I think. Their age at the time in which the outcome variable was measured, which is, as you can see here, people are in their 30s and 40s, and the quarter in which they were born. And you might seem like, well, what does the quarter in which you're born have to do with anything except when do you celebrate your birthday? And even that, like the quarter is not specific enough. You need to know the actual date. Well, Reason why they did this is because different states have different rules as to how old you need to be by which date in order to drop out of high school. So let's just say 50 different states have 50 different rules, but let's just say we're in a state that says you can't drop out of high school unless you're 16 by September 1st of the start of the school year. Or nowadays, high schoolers start more like August 1st. Well, let's say there's a rule that says you can't drop out unless you've turned 16 by the start of the school year for that. And so there are some people who would have dropped out like before their junior year of high school if they had been born just a little bit earlier. But they were actually born 15, 16 years prior, obviously, but like a little bit after the cutoff. And so they were only 15 and like 300 something days when their sophomore year started. And so they have to finish their sophomore year before they can drop out. But if they'd been born like a little bit earlier or on time or whatever, they could have dropped out before even starting their sophomore year or their junior year, whatever it is. And so which quarter you're born in, which seems otherwise arbitrary, affects who can drop out of high school when. And thus it induces some variations, often referred to as random. It's really just more arbitrary in that some people are sort of forced to complete another year of high school before they can drop out by virtue of their birth timing and how it interacts with state laws as to when you can drop out. And probably there's some people who are like, I want to drop out from high school, but I'm not quite old enough, so I'll just like get through my sophomore year or whatever. And then like they start to really like school when they're a sophomore, and they're like, okay, well I'll stick around and graduate from high school. And then they graduate from high school and they go on to college, and maybe they get a PhD eventually, but because they had this epiphany during the year of high school that they didn't really want to be there when it started. Or whatever. So maybe this birth quarter thing induces some fairly arbitrary variation in how much schooling people attain, and that allows us, or them, to use two-stage least squares, Engers and Kruger, to use two-stage least squares to estimate the causal effect of staying in high school for one more year when you really want to drop out. So it shouldn't be extrapolated to the causal effect of one more year of education more generally or in other contexts. This is really what's known as a local average treatment effect. So the causal effect of being born slightly too late in order to drop out of high school when you want to, and so now you have to stay a year more than what you otherwise would. So that is a decent, I'd say by the standards of the literature, setup for instrumental variables. It's certainly clever. In other circumstances, you might have something that is like legit randomized by nature, or not nature, but governments usually. So another classic example of this that involved Josh Angrist and other people, Don Rubin and whatnot, was the randomization due to who got drafted to go to Vietnam. And so they literally did draw like numbers. And so some people had to cut their education short because they got drafted and they had to go to war, and they may or may not have continued their education, when they came back, or they may not have come back alive. But anyway, those that did come back, then they could estimate their earnings annually or whatever after they came back. using instrumental variable based on the randomness of the Vietnam War. And there's criticisms of that too, but a lot of times, researchers in economics go around looking for something that is randomized in nature, by nature, or otherwise has some very arbitrary deal to it. Kind of like the question on the midterm about the French municipalities and like which political system they have. They have a completely arbitrary French rule as to which system you have to have based on whether your municipality has more or less than 3,000 people in it. So anyway, like the modus operandi of a lot of economics is go around looking for variation that is either randomized or otherwise just completely ridiculous in ways that people couldn't really like anticipate, being on one side or whatever. And then when you have that variation, then look to see what outcome does that maybe explain. Anyway, so this was clever. And then we can actually use two-stage least squares to estimate the causal effect of one additional year of schooling among people who were motivated to drop out, and we get a point estimate of 0.129. Remember, the outcome is in log of weekly wages, and so we can think of this as like almost a 13% increase in log wages as a result of that, or at least we could, unless we look 3 or 4 columns over to our trusty p-value, which is 0.0587. So close. But, if we were really committed to this idea of controlling the type 1 error rate, we would fail to reject the null hypothesis that the causal effect of schooling is 0. And thus, we proceed as if the causal effect of additional year of schooling is 0 for the purpose of, whatever. But it's not actually what happens in reality. When people get a p-value of 0.0587, they don't just say, okay, we failed to reject the null hypothesis that the causal effect of schooling is 0. They're like, we reject the null hypothesis that the causal effect of schooling is 0 at the 0.1 level. Or this is marginally significant, suggestive, whatever. And yeah, there's some justification, like no one thinks having more schooling has a negative relationship with wages, log wages. So yeah, maybe we could get away with a one-tailed test. So we would reject the null hypothesis that the causal effect of schooling is 0 in favor of the one-sided alternative that the causal effect of schooling is positive. And if researchers stopped there, it wouldn't be the worst thing in the world. But for economic or otherwise scientific research, it's totally insufficient to say we reject the null hypothesis that the causal effect of schooling is 0 in favor of the one-sided alternative hypothesis that the causal effect of schooling is positive. Because no one really, is interested exactly in like, is this positive or negative or whatever. They want to know how big of an effect it is. And so what I call mud frequentism, or frequentism in practice, is like, well, proceed as if the coefficient is 0 unless you reject the null hypothesis that the coefficient is 0. But if you reject the null hypothesis that the coefficient is 0, and like this is the invitation for p-hacking, but let's just set that aside for right now. But if you reject the null hypothesis that the coefficient is 0, then proceed as if the true parameter is the point estimate. 13%. And so we're in this like very weird situation that if we decide to fail to reject the null hypothesis, we're going to proceed as if this is 0. And if like we do something to get this down, or we do a one-sided of whatever it is, then we're going to proceed as if it's 13%. Nothing in the middle, 0 or 13% for an additional unit of score. And then another thing that, frequentist means in practice, okay, let's calculate the 95 or the 90% confidence interval. Because, that sounds like it's not a number. Oh, come on. He said this kind of the scientific notation, so I don't like that. Okay, so another thing that we're going to do, or not we're going to do, but frequentists do, that is in no way, shape, or form frequentist, which is to take confidence intervals as created by Neyman and interpret them as if they were posterior credible intervals, assuming the posterior distribution to be normal, just because. And a lot of people say, well, what's wrong with that? Okay, it's approximation to a Bayesian thing, but if that's what these people can do, then, more power to them or whatever. So we end up with this quasi Bayesian estimate that there's a 90% probability that the true causal effect of schooling one additional year among people who otherwise would have dropped out is between 1.5% and 24%. %90 chance between 1.5% and 24%. It is almost impossible to put into words how dumb an estimate that is. Anybody with half a brain could have said the causal effect of schooling is between 1.5% and 24% before seeing the data. You don't need R or data or graduate training in econometrics or a degree from anywhere, or you just need a pulse to say the causal effect of anything on wages is between 0 and 24%. Like, from a Bayesian perspective, if your prior on the coefficient of schooling were between, 95% of the probability would be between 0, essentially, and 24%, I would be saying that's way too weak of a prior. It's basically just saying, like, the causal effect is a real number, pretty much. Which we already knew. So if you take this quasi-Bayesian, let's pretend a confidence interval is a Bayesian credible interval perspective on what frequentists do, you end up a lot of times in situations like this with a credible interval estimator that is larger than what your credible interval should have been under the prior. Even conditioning on $35,805 data points. You got something dumber than what anybody's prior would have been. By a lot. Now, economists don't really believe the return to one additional year of high school among people who otherwise would have dropped out is anywhere near 24%. What they really believe is, well, most investments, human capital or otherwise, have a real return closer to like 6%, which is like the historical returns of like the stock market. And if we're talking about, you know, sophomore, junior in high school who doesn't really want to be there in the first place but has to finish out the year because they weren't quite born early enough, then it's probably going to be on the low end of what economists think of as like returns to investments, because, you know, that person probably isn't really learning anything. They're just like killing time until they can drop out. So, you know, you ask economists what they think about the return to like one additional year of high school, but not enough to graduate or get a GED or anything like that, they'd probably be like a 5% at most. So they have beliefs, but they refuse to put those beliefs into the estimate. Okay, well, we could do this rather easily the Bayesian way. With VRMS, so if we just do like this, and then get the prior for the default, have to use this MV bind business to say we have 2, and then we've got you know, all these, and they have different responses, log wage and schooling. And so what we need to do, well, first, okay, we'll put in the exclusion restriction, but as you see here, there's a additional parameter of class rescore for residual correlation, what I've been calling rho, which has LKJ1 prior. That was mentioned in the reading. So let's go into what that is all about. So people in like airports and whatever come up to me and think I invented the LKJ prior. Not true at all. Okay? Lewandowski, Kuro, Fishka, and Joe wrote a paper, it's not even Bayesian, that derived a probability distribution for correlation matrices that is rather simple to use, has one shape parameter and functions a lot like a symmetric beta distribution over -1 to 1. So if that shape parameter is 1, then this PDF over correlation matrices is going to be constant. It's the same value for all valid correlation matrices. And if the shape parameter is greater than 1, then the PDF is going to be kind of like U-shaped, upside down U-shaped, with a mode on the identity matrix. So mode, all the correlations are 0, but they're allowed to randomly depart from 0. So anyway, Lewandowski, Kurofishka, and Joe derived this probability distribution for correlation matrices. What I did was come up with the name LKJ for the distribution that Lewandowski, Kurofishka, and Joe derived. And that's because me and Bob Carpenter couldn't spell Lewandowski Kurofishka, who I was pronouncing as like Kurowicka in 2009, but it's actually Polish, and she's actually a woman, which I did not see coming. And we couldn't spell Lewandowski, Kurofishka, and Joe, so we started calling this distribution LKJ because we recognized that it would be useful for this Bayesian software that we were starting to build at the time called STAN, because it would allow you, particularly in these multi-level models, to specify a prior on the correlation matrix using the distribution here, and a separate prior on the standard deviations, and you could compose those together to get an implied distribution on the covariances, which is correlation times standard deviation of I times standard deviation of J. And the covariances are otherwise difficult to deal with or get a reasonable distribution on. things like that. They were doing this in the 1990s with a distribution called Wishart, or inverse Wishart for the covariance matrix, which is valid, but it's like a disaster to work with. And your beliefs about the correlations are not separable from your beliefs about the standard deviations, etc. And so when Stan first came out and it included this distribution, which we actually called LKJ, then people started like using it and learning about it and not realizing what LKJ stands for, which is the name of the authors who actually came up with it, not like it was some genius invention on the part of Stan developers. It was just we couldn't spell the names of the people who actually invented this probability distribution. But it was fortunate that they did, because it works out well in the Bayesian context. So to specify the priors on this, usual stuff, except we need to put a prior that's constant on 0 for the effect of birth quarter on log wage. So that's the exclusion restriction. When you were born has no effect on wages except through this high school dropout mechanism. And then we need a pretty informative prior on the second, third, and fourth quarter. So you're less likely to be able to drop out sooner if you were born in the second, third, or fourth quarter than you would be if you were born in the first quarter of whatever year you were. You're more likely to be old enough to drop out sooner if you were born in January than if you were born in December of the same year. And then, regular stuff. The default prior LKJ1, like I said, it's flat over the space of correlations. In this case, there's just a 2x2 correlation matrix that only has one free correlation parameter in it. But you could also go a little bit higher than 1 to get the upside down U shape, which has a peak at 0, and unlikely or impossible to be plus or minus 1. So we don't really think the errors between these two things are perfectly correlated. More likely to be close to 0 than to be close to 1. Then we get back a posterior distribution. This does take a while to run, but we can then just get the draws as a tibble, make delta, our S posterior distribution beliefs about the causal effect, by taking sigma of the outcome divided by sigma of the schooling and multiplying by the posterior draws. All this of the residual correlation. So to do what it is that I said could be done here, the way I said to do it. And then if you get this and you plot it, you get posterior density of all these, which is like centered at about 6.5 and ranges between 6 and 7, basically. So in the end, you get something that's mostly consistent with what economists actually believed, but refused to put into their estimator via the priors. And to say, okay, I'm sure, or I'm 90% sure that the causal effect of an additional year of schooling for someone who wants to drop out of high school anyway is between like 6 and 7%, is a much, much, much less stupid answer than I'm 90% sure is between 0 and 24%. Now the reason why this didn't come out great, like I said, it depends on it came out great with BRMS. That's right. Reason why it didn't come out great when I used two-stage least squares to do this frequentist stuff is because the quarter in which you're born is not that strongly related to how much schooling you ultimately take. There's a lot of other factors that go into it, inclusive, among other things, how much schooling your parents can afford to purchase for you. And, you know, that's correlated with a lot of other things that affect your wages and compound. So the birth order makes a little bit of a difference, but not that much. And this paper in particular spawned a lot of research on the so-called weak instruments problem. And this basically says when your instruments are not that great a predictor of the outcome variable, conditional on all the other stuff, then the behavior of the estimator in finite data sets, even finite data sets with 35,805 people in them, is ridiculous. You know, it doesn't have a finite expectation. It has this multimodal distribution across data sets. It has huge, heavy tables. And so when you use two-stage least squares in the presence of weak, like valid but weak-ish instruments, you get a highly variable point estimate. So sometimes it's super big, positive, sometimes it's super big, negative. It's just all over the place. And this is an example of something where with a different group of 35,000 people, it might have landed on -4%. A different group of 35,000 people, it might have landed on 20%. Like, it's just all over the place. And it's not super precise, even at the best of circumstances, and it's far from normally distributed with finite data. And those concern, like, you want that instrument to be as strong as possible, but they don't invalidate the Bayesian estimator. If you have like not super great strong instruments, then you're more likely to get a posterior distribution of delta that is like way spread out. But you would just, you know, have the right posterior beliefs based on that, as opposed to it, really messes up what economists want to do, which is just like test the null hypothesis that the causal effect is 0, and if you reject the null hypothesis that the causal effect is 0, then you have a publishable paper in like Journal of Applied Econometrics or whatever. So Bayesian estimator of instrumental variable models, particularly if you're responsible about putting priors, informative priors, on the things, is a better estimator of the causal effects of these things than the two-stage least squares estimator is. And you get the uncertainty from all the drugs that you can then push through to the predictions and like, is this worthwhile to scale up this intervention on a much larger scale? All sorts of things like that. So this two-stage least squares, I said it was like bowling, and it is. But it's kind of an example of hierarchical data. So we've got like a marginal, you could say, distribution for the first stage, and then a conditional distribution for the second stage. And so we can and we do something extraordinarily similar in other contexts. Bayesians do with hierarchical models, where we use this like marginal and then conditional construct on parameters rather than data. But as you've undoubtedly seen by now, Bayesians treat the probability of observable data the same way we treat probability of unobservable parameters. We use the same probability framework for everything, irrespective of whether this is like observable or not observable. And so that sort of leads to Montgomery. This is not quite the last chapter of the book, but it's close to the last chapter of the book, circling back to what he said in the first chapter of the book, which is Bayesian hierarchical models should really be the default. You would need a strong theoretical and probably empirical reason to use a flat model when you can use a hierarchical model that has several advantages, 4 of which are mentioned explicitly, that you get improved estimate when you have multiple samples on the same big units. If some big units have more observations than others, the hierarchical model automatically adjusts to that, so you get more precision on the A and the B for big groups with a lot of observations, and less precision for the A and the B for the small groups. For the big groups with not very many observations, you automatically get more uncertainty on those. You get estimates of the sigma across groups, or the rho for the correlation in the A's and the B's across groups, which can, particularly with that rho, really help you get a more narrow posterior distribution. And it allows you to avoid averaging, which is something that you see a lot, particularly in the social sciences. People, they have a bunch of indicators or something that are all terrible. And they're like, well, I'll just take an average of those and throw them in the model, or I'll model that as the outcome. Whereas with the hierarchical model, you can model the rawest form of the data and propagate your uncertainty from these terrible measures that you have of whatever construct it is you're talking about to the parameters, the predictions, the utility. It goes all the way through. So yeah, this is very common in social science. Maybe more so in psychology, sociology, or whatever, where they're just like, we'll take an average of a whole bunch of bad measures of the construct and then pretend that's a good measure of the construct. When really we should be propagating our uncertainty as to how good or bad these measures are through it. And Miguel already kind of mentions it, but it's not really his style to like jump up and down and harp on it. But maximum likelihood estimators of hierarchical models are pretty bad estimators, even when they're justified by a cluster random statement. And penalized maximum likelihood estimator is not really a whole lot better. It's kind of like what supervised learning would do, because it's a very incomplete summary of this whole probability distribution that you could get if you were to do this with the Bayesian technology. You get a whole summary of something that you can compose through and stuff like that. So we went through the material this semester kind of fast at times, maybe all the times, but we did so that we could, in the semester, get to the hierarchical models that Miguel says should be the default for doing stuff, regressions, all this, in social sciences or really whatever else, like certainly inclusive of epidemiology and evolutionary anthropology and whatever it is Miguel researches. All that, all of science, really, these Bayesian hierarchical models should be the default for these reasons. And if we've gone any slower this semester, we wouldn't be here in the last class, being able to discuss these things. And so, it's kind of a consequence of really only having one semester to get at these things, but that's just what we were dealt. And then Montgomery goes on to talk about the underfitting and the overfitting phenomenon. And so this goes back to the reading and the terminology from Bayes' rules that we saw last week. So-called full, complete pooling models, which is honestly most of the models that we estimated previously this semester. Just like, probability of voting Republican is a function of the person's age and their gender and their income and whatever, and that applies to all people. Those sorts of models, known as complete pooling, tend to underfit the data because they don't allow for the very real possibility. The data generating process is not the same for all people or all groups. There's going to be heterogeneity in anything that social scientists might be interested in doing because people are not homogeneous. Then there's no pooling models, which are extraordinarily favored in some corners of computer science or whatever, where you just like chop up all the data into little pieces, spread that out over your Hadoop cluster, estimate, the average of, whatever it is you're trying to estimate, and this little stratum defined by the intersection of all these things, and do it all in parallel, and then bring it all back, and you get these like no pooling estimates really fast, even for huge data sets. So it's just like basically put blinders on, just look at the stratum in question and do some estimator, whether it's average or do a regression model or a random forest or whatever. And those sorts of things by construction overfit the data that is given to them, tend to predict poorly for new future data, even if that new future data comes from the same process. It sort of mistakes noise for signal within each of those. Straight up. Or you can do Bayesian hierarchical models, often sometimes referred to as partial pooling, which is going to be somewhere in between the two extremes of no pooling, which underfits, and or complete pooling, which underfits, no pooling. This one underfits, this one overfits, and the Bayesian one is in the middle, and we're going to estimate the degree of pooling along with everything else conditional on the data that is available to us. And then when we do predictions and other things like that, we're going to marginalize over the remaining uncertainty that we have. But it's going to propagate that uncertainty through the predictions, the utility, the decision we make to maximize expected utility, etc. Now, you might say, well, okay, it could be one of these two extremes, it could be somewhere in the middle is the best one. You might want to do, or you might think you want to do Lou model weights. Estimate a fully pooled model, estimate a no pool model, use BRMS or RCNR to estimate a partial pool model, and then get Lou model weights to find 3 non-negative weights that add up to 1 that you could use to weight each of these 3 models to yield a composite which has the highest ELPD. And, go ahead, do that. What you're going to find is like 98% of the weight gets put on the Bayesian partial pooling hierarchical model. But, you got to find that out for yourself like a few times before you start to realize, well, it's that way by construction, basically. And these Bayesian hierarchical models do a much better job of predicting future data than either the underfitting fully pooled model or the underfitting whatever, either of the other two. So warnings. Actually, I should have mentioned this earlier in the semester. Well, one, I left a whole bunch of warnings here. But in the first model that I did, I passed adapt delta in a higher value than the default of 0.8 to eliminate divergent transitions. And so this was talked about in the reading as well. And McElreath correctly, although he's like yelling at clouds for the most part, it's a good thing that Stan warns you when things are not going well, because other algorithms, including the Bayesian ones from the 1990s or whatever, didn't go well, but they didn't produce the warnings. And so you should meet these, particularly the one about divergent transitions. And that means, like I was talking about, Stan has to take little steps to get around the posterior distribution. And if the posterior distribution density or the logarithm of it is changing too rapidly, then even taking little steps causes you to miss some of the posterior mass there. And if you are taking steps that are like a little bit too big, and then you take another step that's a little bit too big, and you take another step that's a little bit too big, you take more and more steps, and eventually you just go off instead of U-turning. And we can tell when this happens under the physics of Hamiltonian Monte Carlo, because in principle that should conserve energy between kinetic energy and the other energy, potential energy. And so when we come at the end of the iteration and we see that that's not true, we're like, okay, something went wrong on this iteration, and we can throw that away. And to deal with that, you can either increase the adapt delta above the default value of 0.8, which causes Stan to take smaller steps, although it takes longer. Or you can change the model, perhaps making more informative priors. Now, I would say that's really kind of only the case if you put in priors that you knew were entirely too weak because of audience considerations or something like that. But usually if you start off by putting in like what you really think as the priors and you check them with the prior predictive distribution checks and stuff like that, then you don't really have much of a problem with divergence transitions anyway. And if you do, you can tweak the adapt delta a little bit and you get rid of it. But particularly if you've got splines and stuff going on, it's easy to not put in enough prior information in order to make the posterior distribution not changing too rapidly, which Stan has problems with it unless it knows that it needs to be taking smaller steps. And so if you're taking smaller steps, sometimes you hit the maximum tree depth. So this by default is 10, which means every iteration Stan will take up to 2 to the 10th steps in like all different directions. But sometimes it has 2 to the 10th steps and it hasn't hit the U-turn point yet. It's still going out. It hasn't diverged, it just hasn't reached the U-turn point yet because it's taking these little tiny steps. And when that happens, you can increase the value of max tree depth, although that will double the amount of time. Just going from 10 to 11 means it doubles if it's hitting the max tree depth. Another warning that you'll sometimes see, bolt/tail effective sample size is too low. In that situation, there's positive autocorrelation on some of the dimensions that's too high, and so the effective sample size is kind of low and not great for making inferences. You can increase the number of iterations after warm-up or the number of chains that you do, particularly if you have extra cores on your computer. That doesn't really take additional time to add more chains, and you get more effective sample size. But in this situation, it means your model may not be super great in the first place. But you kind of need like a good number of effective draws in order to do the posterior predictive checks and ascertain that for yourself. R hat greater than 1.01, this really means the chains haven't converged. But honestly, I don't really look at this diagnostic or any of those trace plots that you see very much, because if I have a problem with my chains not converging, one, I'm going to get all the other warnings, and two, if Stan can't converge to the posterior distribution from different starting points, the posterior distribution has a deeper problem, because Stan can converge to almost any half-decently well-specified posterior distribution, so you probably are not even achieving that. Last warning, you might get low Bayesian fraction of information. This means that your posterior distribution has really extreme heavy tails that it's having a hard time getting all the way out into. So you could try running the chains longer. That's kind of a band-aid. You could really think, okay, are these really my priors? Do I think it could be out that far? But if you can't get rid of that warning, then I would be really skeptical about anything like the mean or the variance or whatever that is sensitive to the tails. You want to be focusing more of your posterior inference on the median and the quantiles. That would be less effective for that. Okay, so some stuff we're not going to have time to get to in order to briefly mention the final. So that's going to be on Tuesday, not this upcoming Tuesday, but the one after that. It will be from 410 to 7, not 6. It will be in IB 270B, not here. 270B is by my office, and there's a link on the syllabus that has a video for how to navigate the hallways in order to get down to the basement where my office is. This upcoming Tuesday, recitation will be a review session. Final exam, similar in format. Obviously covered way more stuff that can be tested in 2 hours and 50 minutes. Plenty of material since the midterm to ask questions about. But everything after the midterm is built on the foundation we started building before the midterm. So it's not as if you're allowed to not know what we did before the midterm. So in that sense, I would say the final is cumulative. So last thing in this last class for the semester, what can we do next? There's a couple Bayesian-ish courses at Columbia. So John Paisley is teaching this Bayesian models and machine learning in the electrical engineering and computer science school in the fall. Some people who have taken this class have gone on to take this one with varying degrees of success. It does not use STAN, but heavily emphasizes coding yourself, other algorithms to do Bayesian-like things, but definitely in the context where prediction is prioritized over integration. I don't know when Andrew Gilman is going to be next teaching his PhD class in the stat department on Bayesian stuff. Probably next spring. It's not in the fall. But whenever that is, you're ready for that, even if you're not in a PhD program. So those are at Columbia. Jonah Gabry, former QMSS student and my co-partner on the thing that I have to disclose about, is doing a STAN workshop at the New York Art Conference on July 11th and 12th. That costs money, like a lot of money, but you could do that. It will presumably cover how to do some stuff in the STAN language, not just VRMS. So although if you have to pay, it is a good next step. Also, the STAN conference is going on June 20th through 23rd. You have to register by April 30th. They do have some money to fund travel for students, so you can just go and listen. I don't think you're really in a position quite yet to present anything there, but you can hear people who are, and that's at the end of June at Washington University in St. Louis. And I hear the weather is lovely there this time of year. So that's it for these. We'll have one more review session on Tuesday, this upcoming Tuesday, and then the final exam a week after this upcoming Tuesday. But certainly, keep asking questions on Ed discussion. Had a good discussion of some stuff today. Honestly, I wish we'd had more of those discussions, over the course of the semester, but certainly people bringing together ideas that they've kind of accumulated over the semester has, really generated some good thoughts and whatnot. So with that, we'll end the stream. We will